By way of introduction today, I want to sort of give you a big picture of where we've come so far through this class. So you might remember right at the very beginning of the class, we did concurrent force systems, and we found some unknown forces a lot of times with equilibrium equations for concurrent force systems. From there, we went on and looked at stresses that happen in kind of very simple mechanical connections. And from there, we went on and looked at deformations of simply loaded structures where they were basically axially loaded. You might remember that term, axially loaded. Anyway, all of those topics that we did right there at the beginning mostly had to do with axial loads, loads that were applied along the axis of a member, right? And we looked at both stress and deformation that could occur in those scenarios. Okay, then we took a little detour after that and we looked at trusses. Trusses were structures that were made entirely of members that are only axially loaded, right? You have an entire structure made of things that individually each member is only axially loaded, okay? That took us up to the first test. Then we went after the second test and we started with frames and machines. And frames and machines were different because members in frames and machines could have more than two forces acting on them, and therefore the members, some of the members in frames and machines, end up having to carry bending moments. And we gave a name for those kinds of members. They're called beams, right? A member that's designed to be able to carry a bending moment. And so now we have these things that are not just carrying axial load, they're carrying this flexure. And after we covered that for frames and machines, basically from there, it took us a little bit of effort for us to be able to define how much stress was going to be felt in a member that was experiencing flexure. So we had to actually do several things, including the discussion on centroids, including the discussion on flexural stress, including shear and bending moments and shear and bending moment diagrams, including being able to find your second moment of area for complex shapes, and then finally, you know, how to be able to design a beam so that it could withstand the kind of bending moment that it needs to carry. So that, in just a couple of minutes, is an overview of where we've come so far in the class. Okay? Now, if you were really sort of able to follow along with that, you might be able to predict what the next thing is that we would want to do in this class, because when we were doing axially loaded members, we started with stress and then we did deformation, like how they were able to stretch under the loads that were being applied to them. That's basically where we're going today for the question of flexure as opposed to the question of axially loading. Does that make sense? So we're looking at situations where a beam might be loaded, and we're going to try to be able to calculate how much the beam will actually deform when it's being flexed, right? And it's kind of our last topic of what we're going to do with in the topic of beams, okay? So there's a little bit of theory that we've got to do so that we come up with the equations that matter to us with respect to with respect to this flexure, and that's where I'm starting here. Where I'm starting is actually where we one of the things that we did when we derived our flexure formula to begin with. You might remember we started that discussion with a beam that, due to some combination of loads acting on the beam, it was carrying a bending moment, right? And then we sliced out a little chunk of the beam and said that that little chunk of the beam, you could kind of describe it with this little sector of a circle. And based on that little sector of a circle and the definition of strain, we came up with what the strain would be as a function of where we're located in the cross-section of the beam, as well as what the radius of curvature was of the beam, okay? Now, that's going to be our entry point to start talking about the flexure of these members. In other words, this flexural deformation of these members, because the radius of curvature there is something that has to do with how the beam is deforming. And that's going to be how we get into this, okay? So what I'd like to do here is, from where we're at right here, let me actually take another expression here and say, was there a particular strand along which we had maximum strain? You might see there we have strain in the x direction as a function of y is minus y over rho. where was the strand of material that experienced maximum strain? It was based on a dimension, and it's basically the furthest distance away from the neutral axis, right? So for our problem here, we could maybe define that relative to this axis right here, and it would be this distance right here, and we called that C, right? And so, you know, if we sort of ignore our signs for a second, kind of think of all this in terms of absolute value, then what we could say is that our maximum strain is going to be plugging in that C value in for Y, and it'd be like C over rho, right? Okay, well that's not too bad. Is there something else I could do here? Okay, so just like we did back when we did the flexure formula, I'm going to restrict our discussion now to only cases where it's in its elastic range, right? So if we say that the material is not going to yield, let's not load it up to the point where it begins to yield, okay? And just say that's going to constrain what types of problems that we can actually look at here. Then what can I multiply both sides of this equation by to get the maximum stress instead of the maximum strain? Okay, y'all remember our stress-strain curve? And stress is related to strain in the elastic portion of the curve with what parameter? Modulus of elasticity. And the way that works is if you multiply by that modulus of elasticity on both sides of this expression, then on the left, what does that end up giving us? Stress, right? So this is our maximum stress. Okay, and this is just going to be EC over rho. But we have another expression that we derived for maximum stress as well. What was that expression? I've got it up here actually. We have MC over I for maximum stress. And so one of the things I can do is just go ahead and set this equal to this M, and I'm going to go ahead and leave this M stated as a function of X, times C over I. Okay? So far so good. Let's actually notice here that if I take that little expression, EC over rho is equal to M as a function of X times C over I should be able to solve that thing for, 1 over rho. All right? Rho is a radius of curvature. Sometimes 1 over rho is actually called just curvature. Because if you think about radius of curvature, when radius of curvature gets larger, what does that mean for how curvy the thing is? If the value of the radius gets bigger, then it's actually less curvy, right? If it gets smaller, it actually is a tighter curve. So sometimes 1 over rho is simply just called curvature as opposed to radius of curvature, okay? So I'm going to solve this thing for 1 over rho down below here and say 1 over rho. What can I do with C? Yeah, C is the same in those two expressions, so I should be able to just cancel that. And that leaves me with what? Okay, M is a function of X over EI. Okay? Well, now I have to introduce something that if you covered in calculus, I've actually noticed over the years that if you do cover it in calculus, which I'm not sure you do, if you do, most people forget it. So it's either that you maybe didn't touch on it in calculus or a lot of people forget about it. But there is actually a function that you learn about in calculus that is this 1 over rho parameter. All right, you can describe that in terms of x and y coordinates in an xy plane. All right, but you got to use some derivatives. And here is the function that I won't spend time trying to prove this right now, but the function for 1 over radius in the xy plane is the second derivative of y with respect to x over 1 plus the first derivative of y with respect to x squared, all this to the 3/2. Okay? Now, when you've looked at our problems we've done in the past, we typically set our beam up a particular way. Okay? Like with the example I have up there at the top of the page, before I started loading that beam, how was the beam oriented? Was it aligned with any of my axes? Yeah, it's aligned along my x-axis. So that's kind of what we're going to assume the beam, where it starts. We're going to set up our axes aligned so that the x-axis goes along the length of the beam. That also, coincides with the m of x function that I'm saying I have right there. Well, if that's how it's set up, and furthermore, if you think about when beams deform, like let's say I've got a beam like this and I start deforming it. Does this beam typically deform a lot? Like, in other words, are the slopes of this beam going to reach large values? Right, he says, especially if you don't think about like the structure of a building, structural steel, that kind of thing. You're thinking in your mind of like little tiny deflections, little tiny deformations. Well, if that's kind of what we have in mind, then what you'll see here is that dy dx, this term right here, what is that term going to be close to? 0, right? It's going to be very small. Furthermore, it's a very small number, less than 1, right? A very small number that is squared, which will make it even smaller, right? So what I'm going to suggest here is that it's probably valid for us to take this term and just assume that it's going to be equal to 0 because we have small slopes. Okay? Well, if that's 0, then what does the denominator become? Just 1, and so what we can say here is that the second derivative of y with respect to x is going to be equal to this bending moment as a function of x over the elastic modulus times the second moment of area. Again, that second moment of area is around the neutral axis. I won't necessarily always put that subscript on there, but I'll just mention it, that is still around the neutral axis. Okay? And this is our starting point for understanding what to do to figure out deflections of beams. Okay? Before I move on and start doing that, let me just go ahead and mention that this kind of makes sense. What does the second derivative kind of mean to you graphically? Okay? Yeah, if you have a positive second derivative, what does that mean as far as the shape of your curve? It's concave up, right? And then if you have a negative second derivative, what do you have? It opens downward, right? It's concave opening downward. Okay? And so this actually kind of makes sense. M of x, when it's positive, it's a smiley beam, right? And so it makes sense to us, or it should, that with a positive bending moment, we would have a positive second derivative here. Okay? We good so far? Well, now what I want to do is show you where this goes. So we start with this second derivative equal to m of x over ei. Let's see how we can use that now. Okay? So let's imagine what would happen if I took that expression, second derivative of y with respect to x, set it equal to mx over ei, and I integrated both sides. And I'm going to actually use a different word for that. I'm going to say, what if I take the antiderivative of both sides? And I mean that kind of, some people use this indefinite integral as a way to say the same thing, but it's basically do the opposite of taking a derivative. Okay? So what if I took an antiderivative of both sides of that little equation right there? What would I get on the left? dy dx. I'd have the first derivative now. Okay? Now what would I have to do to the right if I'm going to take the integral, so to speak, of that, the antiderivative? Okay? Well, I can't, until I know what my function is for m of x, there's not much more I can do besides just say you would have to take the integral of it. You'd have to take the antiderivative of it. But I do want to point out one thing. And I'll do this explicitly instead of having it implicitly, said by the fact that I've got that antiderivative there. When you take an antiderivative, what do you have to add? If there's one thing your calculus teacher probably drove home, it's the plus c, right? We need it here too, and it really, really matters, all right? So I'm going to go ahead and mention you take this antiderivative and you add a constant value, and I'm going to call that c1. Okay? What if I took an integral again, took an antiderivative again? What I have here now is y as a function of x, because all of these y's were already a function of x, because that's what we were coming up with, is the second derivative or first derivative, or now the actual curve itself of what shape this beam took on, right? So y of x up there is actually called the elastic curve of the beam. It means it's the shape that the beam takes on as a result of having the loads applied to it. And how do I get it? Okay. What I do here is I take another integral of this stuff that I already took the integral of, right, this indefinite integral, which included the c. And now what do I have to do again? Add another c, because I did another antiderivative. Okay? So what I'm going to show you here is that we're sort of at these different levels of these derivatives, right? Down here we started with something that was related to bending moment. Right? It was bending moment along with a couple of elastic parameters, right? As I move up, to these other ones that I've identified here, what do I get in the next higher row up here? That's slope, right? So, integrating bending moment once gives me slope of the beam. Integrating again gives me, what I called it a second ago, is the elastic curve. Right? Which is basically, sometimes we call this a formula for the deflection of the beam. Okay? Good stuff so far. Now, you'll notice I've got a couple of entries below where I started with my second derivative there. What do you think I'm planning on doing there? What if I take the derivative of both sides of this function? On the left, I get what? The third derivative of y with respect to x. And what happens if I take the derivative of m of x? Let's say e and I are constant for all these discussions, which, by the way, they don't have to be. But we'll just pretend like all of our problems we're going to end up with constant e and I. What'd you say? Okay. You might remember that based on our shear and bending moment diagrams, what was the derivative of the bending moment function? The shear function. If e and I are constant, then we can just say that this is going to be the shear function. What if I integrate again? Or not integrate, take another derivative, I should say. Okay? This ends up being the fourth derivative, y with respect to x. And you might remember that taking a derivative of v of x gave you a distributed load function. So I'm going to call that W of x. Okay? So this is our distributed load. So I need to point something out now that we've got sort of all of these laid out. If I start by giving you a continuous function for the distributed load, right? I give you a function that you can easily take the integral, the antiderivatives of it, for a distributed load over the length of a beam. Can you find the elastic curve of that beam? Okay. How do you do it? Take the integral. Now, my little discussion here, since I started here, I didn't really think about, having any constants below that. But if you start with W of x, then each step you're going to have to add a constant. Right? Now, here's the good news. When you add those constants, there are a lot of times conditions that you can identify for the beam that will tell you, that will inform you about what the values should be of each one of those constants that you have to add as you go along and integrate, each of those steps. All right? So I didn't show them on this chart, but if you start with a W of x, you can go all the way up to the elastic curve, but you're going to have to, add one of these constants each time you do one of those steps. All right? And I can see it in each of your eyes that you are itching. You are eager to do an example where we do some of that integration. That sweet, sweet integration. Okay? And because I don't want to disappoint you, let's find the elastic curve for a cantilever beam that is experiencing a tapered distributed load. Okay? That means that on the left end of this little beam, there is a particular distributed load value of W, and then it tapers off to 0 out at the end of the cantilever beam. Okay? We'll say that we know that the elastic modulus of the beam material is E, and the second moment of area for the beam's cross-section is I, just to have variables for those. The length of the beam is L. We're supposed to find the equation of the elastic curve for the cantilever beam that is loaded like we have it here. Okay? What's the first step? Okay? We need a W function. Okay? So what is a good W function for this thing? So let's think about when x is 0, what should the function's value be? W. When it goes out to an x equal L, what should the value of this function be? Okay? So this, I think I heard someone just say W minus, right, x over L times W. Does that give it to me? So think about that. When x is equal to L, I've got W minus W. X is just, it's a linear change from one to the other. So that pretty much gives it to me there, right? All right, let me do this as well. Okay, let me factor out the W. Is that acceptable? All right. And now what I need to do is start on trying to find the equation of this elastic curve for this cantilever beam that's loaded with this load. First step is? Okay. Yeah, so think about, our equation up here. Right? I've got this EI, so what if I divide through by EI? Okay? So I'll tell you what, I'll do that here. Divide through by EI. Okay, and what I want to do over here is basically apply that EI with the W. So I'll say W over EI. Okay, and what I think I'm indicating here is that this all is going to be equal to the fourth derivative y with respect to x. Okay, so if I want to take it to the third derivative of y with respect to x, what do I need to do? I'm going to take the integral, right? W, E, and I are all constants. Okay? Say what now? L is constant, but I've got it kind of incorporated in there with my little L value. I tell you what, I'm just going to do the integral like this of 1 minus x over L. We're going to be taking the antiderivative with respect to x. Okay? Okay, so what are you saying that again? Say that one more time. Okay, x minus x squared over 2L, right? And you're saying plus C. I'll call that C1. All right? So now, at this point, is there anything I can do to figure out what C should be? What is this third derivative? Shearing force. So we're saying all of this is equal to V of x over EI.
So can we just plug in some x value?
Okay. Do we know anything about shearing force at any particular location along the beam's length? Where do we know something about shearing force? Okay, when x is 0, we might be able to find it. Where it's easier to find it is x equal L. What's my shearing force at x equal L? 0. Okay, so I'll say down here, at x equal L, what I'm going to have here is W over EI times L minus L squared over 2L, right, plus C equals 0. Okay? And what's the only way to make that equal to 0? Okay? C1, right? What we need for the W over EI can't be 0, right? So we need inside the parentheses to be 0 somehow. So we're saying C1, I would say, has to be equal to what? Okay? Yeah, so think about this. This is L squared over 2L. So can I get rid of it like that? Okay. Now what? Okay. Yeah, so C is going to have to be equal to L over 2 minus L, which is going to be negative L over 2. Okay? And so what does this function up here become? C1 is now negative L over 2. Okay, and that was because at x equal L, our shearing function at L, we know is 0 because that's the end of the beam, and there can't be any more shearing force once you get to the end of the beam. Okay? What do you think our next step is? We're going to take another integral, right? If we take another integral of the left side, we go to the second derivative, right? And how do I do that? Okay, I'm going to keep my W over EI here. And now I need to take an integral of x minus x squared over 2L minus L over 2 dx. So what's this give me?
X squared over 2 minus x cubed over 6L minus LX over 2.
Okay, this was what was just suggested. I think that looks pretty good. What else? Plus, we'll call this C2. Okay, and actually, to make this correct, I need to pull over my W over EI as well, right? So what is this equal to? Okay, that second derivative of y with respect to x was m of x over EI. Okay, do I know my bending moment anywhere along the length of this beam? Okay, there's two places where it might be fairly simple for us to find in terms of other things, but the one that I think is easiest to find is at, again, x equal L. Because I get to the end of the beam, there's no more material, there better not be any bending moment happening out on the very tip of the beam. Okay, so we'll do the same thing again. We'll say at x equal L. Okay, we'll find m of L. And we're saying because there's no more material left at the tip of the beam, there's not going to be any bending moment that is going to be able to carry out there at the tip of the beam. And so what do I do with my function up here? Got W over EI is times, I'll substitute in L everywhere I have an x. So I have L squared over 2 minus L cubed over 6L minus L times L over 2 plus C2. And this has to be equal to 0 because m at L is equal to 0. For consistency here, let me turn this blue. Okay, so what do we know in order to make that whole thing 0? C2 has to be, yep, so C2 is going to have to be equal to minus L squared over 2 minus, all right, or plus, excuse me, L squared over 6, right, plus L squared over 2. Okay, so yeah, someone just said this would cancel that, right? And so what do I get for my C2? L squared over 6. Okay. Now that I know C2, I can plug that in right here. And what's my next step? Okay. I got to take another antiderivative. What that will do down here is take me to a slope, dy dx. Okay, this is going to be, again, I'll pull out the w over ei. And I'm going to take an integral here of, okay, x squared over 2 minus x cubed over 6l minus lx over 2 plus L squared over 6. All right. I might need a little more room on this one, so let me start again down here. This is going to be equal to W over EI. And let's actually take this antiderivative. First term will be x cubed over 6 minus, okay, x to the 4th over 24L minus Lx squared over 4 plus, okay, I think L, yeah, L squared x over 6, yeah. All of this, whoop, plus C3. Okay. Now for this one, I don't need to have any sort of an EI or anything like that. For this one, the parameter that I might be able to use in order to find this C3 is just the slope. So my question is, if we go back up to the original problem, is there anywhere where I know the slope of this beam? Yeah, right where it comes out of the wall, we are constraining it from both translation and rotation, which means the piece of material that's just right there next to the wall, we haven't had any space yet to have any other slope but 0. It's going to be horizontal for this beam right there at that point. So what do we say for our conditions in order to be able to find C3 down here? Okay, at x equals 0, okay, dy dx is going to be equal to 0. Okay, so what we'll say then is that 0 is going to be equal to w over ei times what? Okay. Each of those terms, x, x to the 4th, x squared, and x, right? Each of those terms has an x in it. We're plugging a 0 in for each of those, so those all go away. So then that leaves me with just C3. And w and e and I, none of those can be 0. So C3 is 0. All right. What next? One more time. It's like singing the chorus again, right? All right. So we need to take yet another antiderivative. And what we get out of this is going to be the elastic curve. Okay. It's going to be this antiderivative of w over ei. Whoop, I meant to put that like I've done in the other ones, outside of the antiderivative. Okay. And then what do I put in here? X cubed over 6 minus x to the 4th over 24L minus L x squared over 4 plus L squared x over 6. C3 is now 0. All right. And so what this is W over EI. First term. Next term. Okay. Next term. Next term. Okay. So we're just taking our antiderivatives of each of those terms. What else? Okay. Plus C4. Now, do I have anything that would let me know what C4 might be? Okay. I gave you a hint actually just a few minutes ago. At x equals 0, our beam is constrained against rotation and translation, which means our y value, right where the beam exits its support right there, has to be 0. Okay? So what I'll say down here is that at x equals 0, y of 0 is equal to 0. Okay, that's our elastic curve function basically has no deflection right where it comes out of the wall. And based on similar logic to what we just had before, this tells us that C4 also has to be 0. And so what do we conclude now about the equation of our elastic curve? Okay. W over EI times x to the 4th over 24 minus x to the 5th over 120 minus L x cubed over 12 plus L squared x squared over 12. Did I lose an L? Oh, yeah, thank you. Sorry about that. I lost this L in this step right here. Right? And so those of you who are watching carefully could easily tell that because the dimensionality of each one of those terms has to be the same. You think about any of those x's or l's would be measured in some kind of length. Right? That's what those are representing, is some kind of length. And so each one of those terms had better have the same power of length, or else we can't do that sum. Does that make sense? So we needed that L down there, or else we don't have the same power of length in that term, in that sum, as we did for the other ones. Does that make sense? All right. Well, I may have actually already known this. This may have all just been an exercise for you to see what it takes to do an integration problem in order to find your equation of your elastic curve. There might be another place you could find these. There might be a table in the text that has already worked several of these out for you. Right? And if you actually take a quick look there at number 3, does that look kind of like the one we just did? Now, the form of the equation is just a little bit different, but with just a couple of algebraic manipulations, you will see that we basically came up with the same. They pulled out this, x squared, which makes it a little bit harder to see, but what's their highest power of x? X squared And then over here we have an x cubed, right? So just like ours, that's a fifth power of x. Anyway, I won't spend time doing it to prove that what we did is exactly the same as this, but they do end up being equivalent to one another. Okay? And so this is a little bit heartening, right? It means that maybe for our beam problems that we do, we might not have to do a giant integration series of integrations like we just did just now in order to figure out what these equations of the elastic curves might be. All right? Well, so he said, but you might have to take a derivative now and then in order to find some of the other things. Maybe, if what you're given is an elastic curve, right? It actually brings up a really good point. What if I need an equation that gives me slope as a function of x? It doesn't give that to me directly on this chart, right? But all you have to do is just take the derivative of those functions, and that now is your slope function with respect to x, right? And that's not really that bad to take a derivative of those functions. At least I don't think so. Okay? So this is pretty cool. This basically means that if you know the length of your beam and the elastic modulus and the second moment of area of your beam, then any one of these beams that we have in this table, and there's a few others here that, you know, a little bit lower, we can find the equation of the elastic curve along with some other things too. Look at the left column over here. It says slope at the end, right? So that means that at either end of the beam we can figure out what the slope must be for any one of these cases. That one's not so interesting, but for the simply supported cases, it gives you two slopes, one at the left end, one at the right end, where it comes out of the supports. Okay? Also, for any one of these cases, they've figured out what the maximum deflection is, which is often one of the things that you're trying to find is, well, where is it the worst? How's the, you know, where's the lowest it goes, or the most amount of deflection that happens in the beam? And they give that to you for these kind of single load cases in each one of these cases in the table. An interesting thing there, not all of them occur at the center of a span, right? Look at this one right here. You have an off-centered load, right? And it makes sense that where they're saying the maximum deflection is, you're going to have a different value than what the deflection is at the middle of the span, right? Kind of the same thing if I drop a little lower here. Look at case 8. Same thing, right? They have one value for the deflection that happens at the middle of the span and another that is the maximum it experiences, and where it experiences the max is given by this value right here, right? So one of the interesting things there is that this case does not experience the max at the same x-coordinate as for case 5, right? So anyway, very, very handy table. Okay, and if you wanted me to, I could do a little example problem where we plugged and chugged all the values, and we could come up with what the maximum deflection was or what the elastic curve would say or anything like that. But I have something I think better in mind, if you're okay with it. Yes? So his question is there some way that you could take the composite of more than one of these loading scenarios? And I'm glad he thought of that, because that might be what we're about to do. All right? And we're about to do this with a very, very cool principle. This very, very cool principle is called superposition. Some of you may have already taken a circuits class. If you've taken a circuits class, you use the word superposition in there as well, right? And that's why I provided two of these definitions for what superposition means, okay? Notice up there it says, how can this elastic deformation of beams be found using these tabular formulas we just looked at for more complicated load scenarios? In other words, if you've got more than one of those cases at the same time, okay? Superposition. The definition, the most broad definition, says the superposition principle, also known as the superposition property, states that for all linear systems, the net response caused by two or more stimuli is the sum of the responses that would have been caused by each stimulus individually. Okay? And it turns out that these beam questions that I'm doing right here, at least for small deflections, they are linear systems. In other words, you apply, double the load, you're going to see double the deflection, right? Everything's linear in here as long as you assume the small deflections that I assumed earlier when we were working on this, okay? More specifically for what we're doing, I use this other definition here. The principle of superposition simply states that on a linear elastic structure, the combined effect of several loads acting simultaneously is equal to the algebraic sum of the effects of each load acting individually. Okay? And I need to make one really big point about this before we go into our next example. Right? And here it is. When we talk about an effect, okay? Because they use this word effect a few places in here. Right? Effect, several loads, is equal to the algebraic sum of the effects. Up here it says, it uses the word response, but it's kind of the same thing, right? That's the effect that happens from the stimulus. This effect happens at a particular location. Okay, what I mean by this is, if I'm going to sum the effect of one load and another, I have to be summing those effects at the same location. I can't say, I'm going to take this little half-inch that my beam deflected over here and add it to a quarter-inch that my beam deflected over here. If I'm going to add these things together, it has to be at a particular spatial location, right? And that is the only way to do it, because if I'm trying to add a deflection here to a deflection here, right, then that is not the same effect. And so these definitions up here don't work for that. It has to be a deflection at a particular location. Okay? All right. Shall we do an example? Okay, here we have a beam. It's simply supported. It has a 1,000-pound load being applied a little bit off center. Okay, 6 foot to one side, 4 foot to the other side. It also has a 2,000 foot-pound concentrated moment happening at the left end of the beam, clockwise. Okay? And what we're supposed to do is find the deflection at the center of the span for the first part. Part B, we're going to find the slope at the right end of the beam. Part C, we're going to find the equation of the elastic curve for this beam. And then lastly, we're not even going to do the very last part, but we're going to talk about how we would. Okay? How would we go about finding the maximum deflection? All right. You guys are kind of jotting some things down. What's some information I'm going to need? Okay? Yeah, these are a couple pieces of information, right? It's going to be structural steel. And I know the cross-section of this beam is going to be an S4 by 7.7. So those are a couple of pieces of information I'm going to need to go over here and look up. All right, so let's see here. I think it's right here. S4 by 7.7. I don't need S now. I need I, right? I is going to be 6.08 inches to the fourth. And what's E for this structural steel. Structural steel, 29,000 KSI. Okay, 29 million PSI. All right. So I'll put that in here, maybe 29 times 10 to the 6th PSI. Okay. Part A, the deflection at the center of the span. I tell you what, let's go into the table of these different deflections and try to go shopping, right? Let's go find the one that we need. All right? So we get into the table here. There it is. Yes, I'd like a little bit of case 5, right? So we'll grab that one. I'll tell you what, I'm going to take a little screenshot right here. For case 5. Let me drop that on here. And then let me grab a little bit of case. Okay, uh-oh. We don't have one where there's a moment at the left end of the beam. So what do I need to do? Case 8's the closest I've got. So let's think about grabbing case 8 and see if we can modify it for our purposes. Okay? All right? So now what? So let's look at part A. Finding the deflection at the center of the span for case 5 isn't hard, right? What do I need to do? Part A. Y at the center, not max, is given right here. Right? So I'm going to take this as being minus, what's P? 1,000 pounds. Okay. Times B, what's B? For my problem, B is 4 feet, right? Okay, now, we're going to end up with some units kind of questions here. 4 feet. What do you think I might want to do right here at this point? Okay, let me convert this to inches real quick. Right in the middle of that. Okay, then what? 3 times, what's L? Right? L is the sum of A and B, right? So for us, that's going to be 10 feet, 6 foot plus 4 foot. Okay? Again, times 12 inches per foot. That squared minus 4 times B. B, we already looked at, was 4 feet, right? Okay. Let me get 12 inches per foot in there. And then all of that gets squared. All this gets divided by 48 E. E is 29 times 10 to the 6th PSI. And I was 6.08 inches to the 4th. Okay? Now that accounts for the effect of the 1,000 pound load up there. What else do I need to apply? Okay, so let's ask this question. Does it matter which end I put my moment on as to what the deflection is going to be at the middle? Okay, I don't care, right? Because the middle is going to be the same distance from one support as it is from the other support. Right? So I don't really care. So I can actually just, for this question anyway, because the center is the center regardless of which direction I'm coming at it from, I should be able to just apply this equation as is. So I'm going to take what I have there and subtract ml squared over 16 EI. What's m? 2,000 foot-pounds. Okay, let me deal with those feet right away. What's L? Okay, L is 10 feet, 6 foot plus 4 foot, which gives me 10 feet, again, times 12 inches per foot. That's going to be squared, right? Okay, and then the denominator, I've got 16 EI. E is 29 times 10 to the 6th PSI, and I is 6.08. Inches to the 4th. All right. I just need to do all this. So let's do it. Minus 1,000 times 4 times 12 times, let's see, 3 times 10 times 12 squared minus 4 times 4 times 12 squared. All this over 48 times 29 times 10 to the 6th times 6.08. Okay. And that gives me negative, I'm going to do these separately, so that gives me negative 0.19274. Units on that? Okay, we can figure that out real quick. Here I've got pounds per square inch, there I've got inches to the 4th, so that leaves me with like an inches squared in the denominator of the whole thing. In the numerator, I have inches squared for this term right here, so that knocks out my inches squared I had in the denominator, which leaves me over here with just inches, and the pounds in my 1,000 pounds gets knocked out with the pounds in the PSI. So I should be left over with inches. Okay. And then this other portion down here, we should have negative something. Let's figure it out. All right, negative 2,000 times 12 times 10 times 12, all that squared. All this over 16 times 29 times 10 to the 6th times 6.08. Okay, here I've got negative 0.1225 or so. Okay? So overall, this ends up giving me, I had stored that last result into A, so I'll take what I have here and add what I had in A. Okay? 0.3152. Negative 0.3152 inches. All right. Not too bad for part A. You got a question? Two questions.
For the 2,000 foot-pounds, did it matter which direction the moment?
Ah, good question. He said for the 2,000 foot-pounds that we had up there, does it matter what direction it was rotating? And the answer to that is yes, it does, because if it had been reversed, then we wouldn't have had a negative deflection there. We would have had a positive deflection there. So I'm going to give you a couple of pieces of advice here. Don't shut off your intuition. Okay, that's my number one piece of advice. With my 2,000 foot-pounds clockwise here, you know, if you think about a beam where you're applying a 2,000 foot-pound clockwise moment, right? I'll set it up the same way as you guys are looking at it. A clockwise moment over here makes the middle deflect what direction? Downward. So it's a good thing that my number came out to be negative, right? Because that makes sense with the direction that that load was being applied. Okay? So my first piece of advice is don't shut off your intuition. Check those things and make sure that, you know, it goes the direction you thought it would have. Now, let's pretend you have no intuition. Okay? If you have no intuition, is there a way you still could have known that that was okay to do it that way? Okay? Imagine taking yourself and looking at case 8 from the back. Like, in other words, you know, you're going to go behind the projector screen right now and look at case 8. What are you going to see? You're going to see exactly what we have for our problem up here, right? And so it shouldn't matter then at that point, since we're looking at the center of the beam, it shouldn't matter that we have this, with a setup like this versus the one we have for ours, because it will match once you think about looking at it from the back side. Okay? Yes?
On a similar note, for case 3, what do we do if we had it supported on the opposite side?
Okay, his question is, if we had a case 3 and it was supported on the opposite side. Okay? So I think what you're saying is the slope stays the same as it is right now, but it's supported from the opposite end. Do we have a case in here that deals with that? And the answer is we might not. And I will tell you, this table of 8 cases is not exhaustive, right? But it's pretty good. It gives us a lot of things we can do with it, but it's not necessarily exhaustive. So if that's something you need, you are not helpless. What's your response? What should you just immediately say? Yes, I can do that. As long as you can set up a W function, it's just a matter of integrating a few times, and you can make your own function that gives you all of these things. You don't need to even use the table. Okay? So, all right. He wants to know, is that going to be on the test? Right? Which, some of you are familiar with the story of the rich young ruler in Scripture. Right? And the rich young ruler comes to Jesus and he wants to know, what must I do to be saved? Right? And what does Jesus tell him? Keep all the commandments. What does he say? I did that. And Jesus says what? You lack one thing. Sell everything you own, give all you have to the poor, and come follow me. Right? Well, that's not really the point of what I'm saying. The point of what I'm saying is, The point of what I'm saying is this. When students come to me and say, you know, is that going to be on the test? What I hear them say is, what must I do to get A? And the point of the story in the Bible is the same as my point, actually. Because the man who came to Jesus came to him with a way of saying, what's the bare minimum, dude? And what does Jesus say? If you have an attitude that is what's the bare minimum, then maybe you're not going to make it. That's the point of that story. What's that? He says you can't put your full 100% into every class. Okay? I get that. You're dividing your time. Everyone divides their time. All right? That doesn't mean you have to divide your passion. Everything that you do, you can be equally passionate about. So, anyway, that was a diversion, but let's get back into it. Part B, the slope at the right end of the beam. Okay? So, this one might end up being a little trickier, believe it or not. Okay? Here's what I mean by that. We can go ahead and get the slope at the right end of the beam for case 5. That's not too bad. Actually, I tell you what, for this next one, I'm going to slide all this down and work it up here because I think that will be a little bit easier. Okay? So we're going to find the slope. They use theta for slope right here. This confuses a lot of people. All right? They're like, well, what is that? Is that an angle? Theta means angle, right? Okay? We a lot of times use theta for angles, and there may be a reason they're using theta here, because it actually looks a little bit like an angle there, the way they have it defined. Let me ask you this. If we're measuring theta in radians, does it matter if we're measuring theta in radians and if theta is very small, which it will be for these kinds of questions typically? Does it matter whether we're talking about radians or slope? Here's what I mean. The definition of a radian is a radius over an arc length. Right? So let's say that little arc length right there is, I'll just say A. Okay? So we're going to say that theta right here is going to be equal to A over R. Now let's think about this as a slope. Slope is a rise over a run. Okay? If this is a tiny, tiny angle right here, there is no difference. Okay? So that may be why they're using a theta right there. Anyway, it's a slope. It's a rise over run, but if it's really small, you can kind of think of it as an angle in radians. Does that make sense? Okay, so let's say we're finding this at the right end of the beam. I'll use theta sub r like this. Okay? Case 5 says that the slope at the right end of the beam is going to be theta 2, right? And that's just going to be equal to PA times L squared minus A squared. So P again is 1,000 pounds. A is 6 feet, 12 inches per foot. Okay. Here I'm going to have L squared minus A squared. Okay, 10 feet times 12 inches per foot. All that squared. Give myself a little more room here. Okay. L squared minus A squared, right? I'm dealing with this one right here. So L squared minus A squared, 6 feet, times 12 inches per foot. Whoop, let me do it this way. Okay, all this over 6 times E times, I guess I missed L in there too, right? 10 foot times 12 inches per foot. And then I also need to get I, 6.08 times 10, not times 10, 6.08 inches to the fourth. Okay, positive, right? Should that slope be positive? Basically, I'm following exactly what's in the table there, right? So it looks like that should be right. It should be positive, just like I have it. Okay, what then? Okay, now this one's a little different. Should I use theta 1 or theta 2? Okay, here's what you got to do again. You got to imagine yourself going behind this projector screen and looking at this situation, because that's actually what we have, right? And when you look at that, the dimension that we're going to want is actually labeled theta 1 right there. And it's not going to be negative, it's going to be positive. Okay? So we're going to use this one right here to match our situation, right? And we're going to, instead of making it negative, we're going to make it positive. So let's do ml over 6EI, and we're going to add m, 2,000 foot-pounds, 12 inches per foot. Okay. L is again going to be 10 feet. We get another 12 inches per foot in there. All this divided by 6EI. 6 times E times I. 6.08 inches to the fourth. Okay. Now let's see if we can put all this in there. All right, 1,000 times 6 times 12 times, I'm just going to go ahead and put these in here. 10 times 12 is 120. Squared, 6 times 12 is what? 72. Squared. Okay, in the denominator, let me put 6 times 29 times 10 to the 6th times 120. Whoops. Times 6.08. I guess I'll do it the same way I did before and get this one first. Okay, so this will be 5.227. Okay, times 10 to the minus 3. Units. Slope is unitless, right? So we don't need to add any units there. It does turn out positive, which is good because that's what we're expecting there at the right end of the beam. All right, let me store this. I'm going to store it into B. Okay, now let me do the next one. 2,000 times, okay, 12 times 120. all this divided by 6 times 29 times 10 to the 6th times 6.08. .722 times 10 to the minus third. Okay, that's this. I should move this a little bit. Okay, that's for this other term. And so total, I'll take what I have there and add it to what I just stored into B a second ago. This will give me 7.949 times 10 to the minus third as my slope. All right. The next one's actually easier, believe it or not. We need to find the equation of the elastic curve. And there's really only one tricky thing about this. Okay? All we do when we find equations of elastic curves out of these tables, we just add them together. We add one function to the other function. And you have the equation of the elastic curve, because they're both with respect to x. And if they're with respect to the same x, you can just add the two together, and it gives you your total equation of your elastic curve. Okay? But that's where the trickiness comes in for this problem. Because the x that I have for case 8 is not the same x that I have for case 5 for my situation. Notice that? Okay. Case 5 matches perfectly with what my situation is, so I can use case 5, no big deal. Right? Case 8, though, is reversed from my situation. So how do I come up with an equation that would be with respect to the x value that I would presume for my problem, right? This is what I'm presuming for my problem, is that I've got x along the length relative to the left end, just like case 5 has. Okay? Yeah, so think about it this way. Let's say I've got this beam, and it's got its reactions at the ends. Okay, I've got this. This is what the case currently, the case for case 8 does. And it says that my locations along the length are going to be called x. Okay. Now, I've been saying this, but again, we need to think in our minds, what would I do if I looked at that from behind the projector screen? Right? Another way I can do that is I can take this thing and I can flip it. That's like what I have, right? But you'll notice x is now measured over here. L was here. L is still there. How do I come up with, I no longer have x right here, even though x was what I had in the other case. I need to have something that gives me an x right here. Okay? So, x goes to L minus x. And when that happens, what happens with my equation of my elastic curve? Y is going to be equal to minus m times what? L minus x over 6 E I L times L squared minus L minus X squared. Okay? And that's what it would give to me if I flipped this around to the direction that I have for my case. All right? What?
So when you flip the beam, like in part B,
Yeah.
flip the diagram under it that shows what the beam does in that instance.
For part B, the only thing I needed to do for part B was notice that it was enough for me to look at the opposite end from where the moment was being applied, and that would give me the slope. It'd be the same thing, you know, just negated and at the opposite end, right? So that's, instead of using theta 2 directly like I would have, I said, no, really what I need is the one that's opposite of where the moment's being applied, and I don't need this negative sign, which is, that's what you get by just viewing this from the back side. You don't need to actually line it up with any x coordinate or anything like that. You're just noticing that is the orientation that gives you that parameter that you're looking for. Okay? What we had to do here is basically starting from the same mentality, but we had to be a little more formal about it because we needed a coordinate, not just a particular location. Right? So in order to get that coordinate, we had to understand how to transform the x that was given on their figure, right? Their x is given like to some location relative to that end. We just needed to flip it around so that we could end up getting the x coordinate relative to the opposite end. Okay? And that's where we got this formula right here. All right, well, once we've got that, you know, we could write it down. You know, it's not going to blow anyone's world or anything, blow anyone's mind, I don't think. Let me do it up here. Basically, all we're going to do is say y, this is part C, y is going to be equal to minus, P was 1,000 pounds, B was 4 feet. Since I'm not going to actually do anything with these calculations, I'm going to forego putting in all of the conversion factors. What was x? It's just x, because we're doing this all in terms of my variable x. 6 e I L was 10 feet times 10 feet squared minus B was 4 feet squared minus x squared. And then all of this, to all of this, we add, or, you know, I guess since it's minus here, we're going to be subtracting, so to speak, 2,000 foot-pounds from the m right there. Here we've got L minus x, so 10 feet minus x, all over 6 e times 29 times 10 to the 6th psi. I is 6.08 inches to the 4th. L is 10 feet. And over here we've got 10 feet squared minus, and then here we've got 10 feet minus x squared. And that is, I mean, we could simplify it down more if we wanted to. We don't have to. That's an expression that gives me the equation of the elastic curve under these two loads. Okay. Now, the last thing we need to discuss. how would we go about finding the maximum deflection? Okay, so the reason this is tricky is that the maximum deflection for case 5 occurs at this x-coordinate. The maximum deflection for case 8 occurs at this coordinate. Of course, you would have to take basically L minus that coordinate, right, because we're flipping it around. Okay. They're not at the same location. So that means I can't take this function right here and add it to this function right here, because they are not at the same location on the beam. As a matter of fact, the location where the maximum occurs is likely neither of those positions. The location where the max occurs is not something you can just easily glance at this thing and know. A lot of people are very tempted to say, well, what if I just take the average between the two? Okay? Like, I don't know. I mean, you got to applaud at least the effort, right, to think about that. But that's not where it's going to be. Okay? How do you go about figuring out where the maximum would occur? Okay? Okay, you're very close. He said find where the shear is 0. I'm going to say find where the slope is 0. And how do I know the slope? What's an equation I could make for the slope of this beam anywhere along the beam? For this thing I just came up with, find the derivative. Set equal to 0. Okay. Then what? Solve for x. That x that you will solve for is going to be the position where you have the maximum deflection. Once you have that maximum deflection, or the location of the maximum deflection, you can take that x value and plug it back into this expression, and that will tell you how far the maximum deflection is in the beam. That makes sense? So that's if you needed to find for one of these where the different effects cause the maximum to be in different locations, then that's what you got to do. You got to find the equation of the elastic curve, take the derivative, set it equal to 0, solve for x, find that x value, plug it back into the main equation, and that gives you your maximum deflection. Yes, sir?
Do we plug it back into the y equation
Right.
we just found?
Correct. Because now you've found the coordinate where it occurs. You take that coordinate, you plug it into your y equation there, and it'll give you the deflection that occurs at that location. Great. You guys stayed with me the whole way. I'm excited. I'm proud of you. So proud of you that I plan on coming back here to see you on Friday.